Now, some of you might be wondering, what is the talk about the various types of clocks? We have the regular clock, which you just check out right now, and as of today, it's around 8:24, and it's kind of like, hey, we actually go through all these particular measurements, and this can be used in various interesting ways in terms of what you want to do at a specific point in time. But now we're getting into conversations about the atomic clock and where you're going from atomic clock to something much deeper. It's quite really fascinating to actually explore that in terms of how quantum physicists or astrophysicists are actually introducing the concept of time. How can we get accurate measurements for time? And this is where this actually article comes in, where it says that nuclear clocks could outdo atomic clocks as the most precise time piece. And I'm really interested to see how this actually plays out. Based on this article, there's so many fascinating things that this article actually points out, and we're going to talk about this in full details. Now, for some of you that don't know what is atomic clock is pretty much based on the use of electrons, and when electrons jump from one energy to another energy level by the use of laser to trigger it. That is a great way to be able to measure accurate time measurements compared to our regular clock that is usually what we see at home. Now, this time is pretty much the basis on other types of devices that are used, like for example GPS, and maybe some of the time that you have on your devices as well. Some of them are based on the atomic clock. And so this is where the nuclear clock comes in. We know various things concerning the specific atom. We know that the atom contains electrons, the protons, and the neutrons, and based on all this, we know that based on those positions, they do have some interesting conversations in terms of the attractions and also how they behave based on their charge and size. We know that the electrons are kind of cloud in that particular electron density space, and in the core, which is where the main mass of the atom is, consists of both the protons and the neutrons. Now, focusing less on the atomic clock, which is based on the electrons movement from one energy to another energy level, we are actually in this case, based on this particular article, focusing on nuclear energy levels. And I'm like, I never heard about that before. To be honest, I've never heard that. I've never heard of the concept that, oh, the nucleus actually has its own energy levels. And to access that is really tricky and really hard because lasers has a specific energy that can be used to excite various particles in an atom, and to excite particles in a nucleus is really difficult for a laser to do that. However, this article actually talks on different things and methods that can be used to excite nuclei in order for we to be able to then begin counting the clock. Now, looking at this article actually puts out some interesting conversations in terms of the electrons based on the atomic clock, and it actually says that using the energy jump of atoms, electrons, according to quantum physics, electrons in atoms can carry only certain amount of energy in specific energy levels. To bump electrons in an atom from one energy level to another, an atomic clock's atom must be hit with a laser light of just the right frequency. Now, that frequency, the rate of oscillation of the light's electromagnetic wave, serves as a highly precise timekeeper. And so this is where this comes into play when some interesting problems actually is introduced. Like for example in here, to tally time in nuclei, which is now focusing on the nuclear clock, we actually need to focus on the ability to set off the jump between the nuclear energy levels with a laser. Now, nuclear levels are not normally accessible with lasers, according to this particular physicist. And in this case here, for a nuclei, that would require light of higher energy than suitable lasers can achieve. Now, luckily, there is one lone exception in all of these known nuclei, and in this case here, they actually discovered this particular, of course, element which you can find in the periodic table, Theorem. And this theorem type is having a nuclei or mass number that is 29. And if you look at the periodic table, you can find the specific atomic number. All you have to do is just for the one that has the closest mass number, or some periodic tables will have, in this case, the atomic mass. So in here, this will be the potential particular nuclei that will have the laser to be able to excite it for we to kick off the jump and count our time pace. So this is really fascinating to see this particular article jump into this particular idea of having a nuclei clock, because of course the nucleus is having a strong nuclear interaction, which is really hard to actually overcome based on the normal lasers, and to be able to figure out what element is actually, or nuclei is suitable for this particular experiment or potential new way of getting a precise time pace is really fascinating in here. And I'm really excited to see a couple of things in here based on a couple of tests that will be determined if the fundamental constant of nature vary over time. Now, for example, some students have suggested that the fine structure constant, a number that sets the strength of electromagnetic interactions, could change, and this nuclear clock is a perfect system to search for variations of fundamental constants. And in here, the device could also test a foundation for Einstein's general theory of relativity called the Equivalence Principle. I don't know what that is. I'm going to check that out and kind of experiment and we'll see what it says. If you click on that, what does it say concerning that? In the first Galileo gravitational experiment is recreated in space. Equivalence principle holds up inside an orbiting satellite. That's pretty cool. There is a satellite right there. No information concerning that. Well, let's go back to the article and get the rest in there. Maybe I'll do my little research on what the equivalence principle is. If anyone has any idea on what that is, you can hit a comment down below and let me hear your thought about the equivalence principle. Or they could search for dark matter exclusive undetected particles that physicists believe account for only most of the universe matter, which could tweak the twinkling of the clock. So pretty much fascinating stuff to me. I'm really excited to know your thought about using a nuclei clock instead of now atomic clock. Which one is actually going to be an accessible way? Of course, according to this could be a potential used to determine an accurate representation of time. I mean, if you're able to break specific subatomic particles into other particles, I mean, are we going to now be doing that as well, subnuclear particles, or we're going to stick with, the nuclear particles as a count for time for our clocks? Otherwise, let me hear your thought about this in the comment section down below about nuclear clocks versus the atomic clock, and how do you think this particular experiment is going to be in terms of the future of counting time, and how are we going to be more accurate? Do you think it's going to make any difference in your life based on how accurate it's going to be, or does it matter at all whether we count in terms of atomic clock to nuclear clock, or our regular clock that we use? Doesn't really matter? Let me hear your thought about this in the comment section down below. Other than that, see you in the next one. Stay smart as always and believe in yourselves.